Hello, everyone. I'm happy to introduce Fadel Adib, who is the Doherty Chair of Ocean Utilization and Associate Professor at the MIT Media Lab and Electrical Engineering and Computer Science Department. He directs the Signal Kinetics group, which invents, builds, and deploys wireless and sensor technologies to address complex problems in society, industry, and ecology. Fadel's research has received many awards, including the NSF Career Award and the ONR Young Investor Award. He was named by the Technology Review as one of the world's top 35 innovators under 35 and by Forbes as 30 under 30. His research was named as one of the 50 ways MIT has transformed computer science, and he was invited to the White House to demo his research to President Obama. Fadel is also an entrepreneur, and his commercialized technologies are used by major hospitals to monitor patients with Alzheimer's, Parkinson's, and COVID-19. Um, please hold your question till the end, and um, yeah, Fadel, it's all yours.
Thank you very much, Coral, for the introduction. Is my screen sharing well?
Yes.
Fantastic. So thank you for your introduction, and thanks to everyone for being here. I'm honored and excited to be here with you today to share with you the work that my team and I have been doing in order to bring the Internet of Things underwater. But before I do that, I want to tell you where I'm coming from and why I believe there's an enormous potential for underwater IoT. I have been working on wireless networks and the Internet of Things for about a decade now. And I've seen IoT grow from a buzzword that academics tended to avoid to a movement that is already transforming many industries. So how big is IoT today, and how many IoT devices are there? As of 2020, there are about 30 billion IoT devices, according to estimates from McKinsey, Deloitte, BCG, and the number doubles every 2 to 3 years. For those of us with electrical engineering background, it's almost as if we have a Moore's law for IoT. And you might be wondering how come IoT is growing so fast? And the reason is quite simple. In today's data-driven world, we need internet-connected sensors in order to get data from the physical world. And this data helps decision-making and prediction. But how much of IoT is underwater? Well, we still don't have really an internet of underwater things. The closest is probably DARPA's Ocean of Things program, which aims to deploy about 6,000 floats on the surface of the ocean. But even those are floating, they're on the surface, and they're not underwater. And the reason is that it's very difficult to bring them underwater. Typical IoT technologies like Bluetooth or Wi-Fi or GPS, none of these work underwater. And we need fundamentally different architectures for underwater IoT. But what if we could build an internet of underwater things? What type of data would we want to collect? And what decisions and predictions can we make? And what new industries would this drive? First, there's enormous scientific value for ocean IoT. As many of you know, more than 80% of the ocean has never been observed or explored. And underwater IoT would allow us to deploy sensors in the ocean and have them transmit information back to us. They may be able to send us back images and sounds of animals so that we may explore the ocean, or of coral reefs so that we can monitor underwater climate. And underwater IoT can also play a key role in food security. According to the United Nations, aquaculture or fish farming will be the fastest growing food sector over the next 30 years, and it is expected to fill in the gap between food supply and food demand around the world. So if we want to feed the world's population, we need to get aquaculture right. And an ocean IoT would allow us to do exactly that, to monitor aquaculture environments in real time, optimize feeding, intervene whenever we detect environmental hazards like algae blooms. And there's many other applications for underwater IoT, ranging from underwater robotics to mining, weather prediction, defense, and disaster response. So we can enable all of these applications if we can build an underwater IoT. But we are not there yet. In fact, less than 1 in a million of IoT is underwater, even though oceans cover more than 70% of our planet. And today I want to share with you my team's work in bringing the Internet of Things underwater. Now, we haven't managed to enable all the applications that I told you about, but what I want to do is share with you exciting progress on two fronts. First, I want to tell you about the fundamental new technologies that we have been inventing, building, and which we are in the process of testing and developing and deploying. These range from an entirely new class of subsea networks that enable batteryless underwater IoT and localization to new technologies for underwater-to-air communications. And second, I want to tell you a little bit about our community and policy outreach initiatives, ranging from things we do locally, like open sourcing our hardware and software, to organizing community-wide events and engaging with policymakers. And the reason we pursue both of these directions, technologies and community and policy, is that we believe that we need to do both in order for us to truly have impact as a community in bringing the Internet of Things underwater and enabling the exciting applications and important ones that I told you about. So let me start by telling you about our work in building a batteryless underwater IoT. Now, a few years ago, as we started thinking about how we can take IoT sensors and deploy them underwater and have them collect information over long periods of time, we faced a problem. And the problem was that the battery life of underwater sensors is extremely limited. So as we look deeper into the problem, we realize that the reason is that underwater transmissions consume significant power. So typically tens to hundreds of watts for today's underwater modems. And not only this, unlike typical IoT sensors, they cannot be recharged easily. In fact, if you want to change a battery and you have a sensor that is deployed in the ocean, you might need to send a research vessel and pay $30,000 to $70,000 a day just to operate that vessel. As a result, state-of-the-art sensors for tracking marine animals mostly last for a few hours or days, after which their batteries die. There's been some research on making ones that can last longer, but even those, they need to start duty cycling, so you can't get much information out of them. And this makes it very difficult to use these sensors for long-term climate sensing or discovering migration patterns of marine animals. And this got us thinking about ways to reduce the energy consumption of underwater communication and networking. And I want to share with you how we are working on overcoming this problem. A few years ago, we developed the first technology that enables underwater batteryless networking. So we developed a technology called underwater backscatter, and this kind of communication technology consumes near zero power, which allows our sensors to operate over very long periods of time without requiring any batteries. And let me describe to you how this technology works at a high level by comparing it to how traditional sensor communications work. Now, in many of these environments, you typically have, for example, an underwater drone or a submarine or a ship that communicates with various sensors. But for simplicity, we'll focus on just one sensor. Now, remember, you cannot use Wi-Fi or Bluetooth to communicate underwater. So to send information to the drone, today's sensors have to use acoustic signals. So the sensor has a speaker and the receiving drone has a hydrophone or an underwater microphone. And to communicate information, the sensor transmits information using sound waves, acoustics, or sound. The problem with this approach is that generating an acoustic signal requires a lot of energy, which drains the sensor's battery. In contrast, our technology does not require the sensor to generate any acoustic signal. Let me tell you how it works. In our design, the speaker and the hydrophone are both at the drone. And the sensor is connected to an acoustic reflector, which for simplicity, you can think of as a mirror. So when the transmitter sends sound, it reaches the sensor and then it reflects back to the receiver. Now, in order to communicate information, all the sensor needs to do is to toggle its reflector between reflective and non-reflective states. And once it can toggle between two states, it can transmit bits of 0 and 1, and that allows it to communicate its sensor data. So to summarize, in traditional communication, a sensor must generate its own acoustic signals, which is power consuming. But in our technology, it just needs to turn a switch on and off. And what we've done here is that we've shifted all the power consumption from the sensor itself to the drone. But because the drone has its own power source, this makes it much easier for us to deploy a larger set of sensors and be able to communicate with them from a privileged location. And of course, this is all great, but there's still one main question, which is how can we control the reflections of acoustic signals? Our idea is to use piezoelectricity to design programmable acoustic reflectors. Now, for those of you who are not familiar, the piezoelectric effect refers to the ability of certain materials to transform mechanical energy into electrical energy. And let me explain to this how this works using a very simplified example. So let us say we have a piezoelectric material like the one you see here, and we try to measure the voltage across its terminals. Now, if a speaker transmits an acoustic signal, the signal travels as a pressure wave, and when it hits the piezoelectric material, the material vibrates, and the vibration creates an electric signal at the terminals of the material. So effectively, the material has transformed mechanical energy, which is sound, into electrical energy, which is voltage. But remember that what I want to do is to turn this material into a reflector. And to do this, we simply add a switch across the terminals of the material. When the switch is open, the material behaves exactly the same as before, and it transforms acoustic signals into electrical signals. Now let us see what happens when the switch is closed. When the switch is...
I'm sorry to interrupt. Your slide is frozen.
I see. Okay. So let me try to stop and reshare again. And if that doesn't work, I will try to log off and then maybe log back on and see if that works.
Okay, thank you.
Thank you very much for letting me know.
Sure.
Are you able to see my screen now?
No.
No.
No?
No.
Okay, I apologize about that. Let me try. This was happening in the tech tests, and it is probably my problem. I have a bandwidth issue on my end, so thanks a lot for bearing with me. What I'm probably going to try to do is to disconnect and then reconnect again. I apologize about that.
Sounds good. Thank you.
Thanks.
Okay, I'm back, and I will try to share my screen again, and hopefully this time it will work. Is it working?
Yep, we can see your desk.
Okay, folks. So I apologize about that. It might happen a few more times, and hopefully not many times. So let me recap where we were. So what I was saying is that what we want to do is we want to be able to use the piezoelectric material as a reflector, and the piezoelectric material can transform mechanical energy, which is sound, into electrical energy. And what we did is that we added a switch. And what I'm saying is that when the switch is closed, I want us to think together about what happens. When the switch is closed, the two terminals of the piezoelectric material are connected to each other, which means that the material cannot vibrate. So when the material cannot vibrate and you have energy coming in, where does this energy go? This energy has to be reflected back. And so by simply opening and closing this switch, we're able to shift between reflective and non-reflective state. And we call this technology piezoacoustic backscatter because it uses the piezoelectric effect to backscatter or reflect acoustic signals. And what is very nice about this is that our sensor now to communicate, it needs something of the order of a few hundreds of microwatts, even for continuous communication, which is 1,000,000 times less than what standard low power acoustic modems require. Not only that, the sensor can also harvest energy in the non-reflector or the absorptive states, and it can power up entirely using this energy, which allows us to make it entirely battery-free. So let me show you a short clip of one of our earliest prototypes in action. At the far end of the pool, you can see a hydrophone receiver and a projector, which is our speaker. And here's our batteryless sensor. It is connected to a circuit.
Fadel, I'm sorry. Yeah. We cannot see the video.
I see. I apologize about that. Let me see if I can. I'm not sure what much more I can do at this point. Will these slides be made available after the presentation? We could do that. Let me try to share my screen. And if that doesn't work, I'll try to reconnect and reconnect. Oh, yeah. Diane always has good ideas. I'll shut off my video and see if that helps. Did my screen get shared this time?
No. You can also send your presentation to me and Coral, and we can share it for you, if that would work.
Okay. So let me do two things. I'll first try one more time, and then I'll log off and then log back on, as Diane said, without the video.
Sure.
Okay.
Sorry for the delay, everyone.
Okay, hello again. It's me. Can you please let me screen share?
Yes.
And this time I will not share my video.
You should be all set.
Here we go.
Good, we can see it.
Okay, great. And towards the end of the talk, just to build some suspense, I will let you know why I have a bad connection, which is usually not standard in Cambridge, Massachusetts. So in the video, at the far end of the video, there's a hydrophone a receiver, and there's a projector. And here you could see a sensor or sensor node connected to the circuit, and the circuit has an LED. So the circuit does not have any battery, but as I play the video, you can see that the LED lights up. And the reason it lights up is because it is able to harvest energy and power up from this energy. Next, let me show you how we can decode the sensor's response. So we used a hydrophone to measure the received signal. And let me show you what we got. Over here, I show the amplitude of the received signal on the y-axis and time on the x-axis. And at about 2.5 seconds, the speaker starts transmitting. So we see a jump in the amplitude from the speaker signal itself. Then around 3 seconds, the node starts backscattering. As you see, the amplitude switches between two levels, which correspond to the backscatter signal. And because the hydrophone can sense these amplitude changes, it can use them to decode the backscatter packets. Now, if you're wondering how come the amplitude does not go all the way to 0 in one of the states, remember that the hydrophone doesn't only get the reflection, but it also gets direct signals from the speaker, which is never 0. So effectively, you can think about the backscatter node applying a code so that it can tease apart the signal that is coming from the sensor node that we care about, but not all the other reflections in the environment. And in our papers, we show how we extend this basic idea with algorithms and techniques that allow us to scale it to many nodes that can operate at the same time and to deal with a lot of other reflections in the environment. So here you could see one of our early sensors that we built. We fabricated and 3D printed omnidirectional transducers We built them in-house, and this is the circuit that we built that allows energy harvesting, bidirectional communication, and even sensor interface. One of the other things that I want to say is that the transducer is omnidirectional, and it can also be designed to be omnidirectional in 3D. The idea that I was talking about before as a reflector, it does not necessarily mean that the reflector has to be directional. It can be omnidirectional. One of the other super cool things about this is that this entire thing costs about $100, and our published work shows that it consumes hundreds of microwatts, which is 1 million times lower power than state-of-the-art underwater modems. And we ran experimental evaluation in the Charles River across different environmental conditions, including snow and rain. So here you could see a couple of my students running experiments at MIT Sailing Pavilion. We tested it at different ranges, throughputs, and number of nodes. And we've demonstrated throughputs up to 20 kilobits per second, communication range up to 62 meters, and up to 10 concurrent nodes before spatial reuse. Now, of course, this leaves a lot to be desired, and which also makes this area very exciting, because in only a couple of years, we were able to reduce the power consumption by many orders of magnitude and boost the communication range by 10 times. And in a little bit, I will tell you what are some of the open problems and opportunities that we can work on moving forward through this technology. But before I do that, I also wanted to share with you some of our recent work about moving from communication to localization, and about how we can enable underwater GPS. Now, we all know that the global positioning system has revolutionized and changed our lives. We use it for a variety of location-based and navigation systems and services. But one of the biggest problems with GPS is that it relies on radio signals, which, similar to Wi-Fi and LTE, do not work underwater. So if you were to take a device and try to use it for underwater positioning, it does not work. And so how do today's systems do underwater positioning? Of course, there's been a lot of work on underwater positioning. And let me tell you about one of the most common conventional techniques for underwater positioning. So let us say that you have a drone like the one you see here, and it wants to localize itself. The way it works is that it tries to measure distances to multiple deployed anchors. So rather than having satellites in space, you have deployed anchors that are underwater. And so the drone, each of these anchors knows its own location, and the drone wants to localize itself with respect to them. So in one of the most common systems, the node transmits an acoustic signal or sound. The sound reaches these anchors, and once it gets to them, they reply immediately with the response. And so what the drone wants to do is it wants to compute the distances to the anchors. And to do this, it uses a simple equation, which is that the distance is equal to the time of flight multiplied by the speed of sound. So what it does is that after it transmits the signal, it measures the time it takes the signal to go and come back. And it uses it to measure the time, and then it multiplies the time by the speed of sound in order for it to get the distance. And once it gets the distance, it is able to locate itself. And even though this is one of the most common approaches for underwater positioning, it does face a few problems. The first one is that when you deploy these anchors, you put in them batteries, and these batteries can run out of energy. And whenever they run out of energy, you need to go back in and replace them, which, as we said earlier, is very expensive. It's very expensive to go into the ocean and have to replace equipment. Other people have tried to build much larger ones with bigger batteries, but then these require very expensive packaging as well. And so these underwater localization systems end up being super expensive today. And the other issue with these approaches is that they're very difficult to scale. It's very difficult to cover the entire ocean with these sensors. And because they're very expensive, that makes it also very challenging to be able to use them. So since batteries were such a big problem, we started thinking about whether we could build a batteryless underwater positioning system. And so the basic idea here is that you have batteryless sensors that are deployed, similar to the ones you see here. And the way they work is that you send a signal, you send an acoustic signal from the drone, and then these sensors will harvest energy so that they can power up and their batteries. And after they power up their batteries, they can then respond to the drone. And the drone can, again, use the same idea in order for it to measure the time, and from the time it can get the distance. And this idea is very exciting, except for one problem. And the problem is that now the time that the drone uses to measure the round-trip distance is not just the round-trip distance, it also includes a random wake-up lag. So remember that these anchors these batteryless sensors need time to power up. And so by the time the signal goes to the node, to these sensors, they need time to power up, and then they reply back. You have a lag that is very difficult to predict. And this random lag also changes depending on the distance. It changes depending on the underwater environments. And it makes it extremely hard to localize, for the drone to localize itself by measuring time. And so to overcome this problem, what we wanted to do is we wanted to use our backscatter sensors as ways for underwater positioning. Remember that the way these sensors work is that, again, you transmit a signal from which they harvest energy to power up. And after they power up, they start replying with modulated reflections. But now, instead of simply measuring the time, what we do is that we try to measure the phase instead of measuring the time. And I will not go into a lot of details, but at a very high level, the phase of the wireless signal, every signal has a phase, which is this angle that changes over time, as you can see here. So it goes up and down over time. And this phase is related to the distance. So if we can capture the phase, which we are able to measure, and we know the wavelength of the signal that is transmitted, then we would be able to measure the distance. Now, as I mentioned, this is the idea at a high level. But what we do in our system is that we use backscatter as a code, and the phase of the continuous signal is not impacted by the wake-up lag. And in our paper, we show that we have a multi-frequency estimation algorithm that allows us to compute the time of flight from backscatter sensors. And we show that it allows us to use it for localization. So let me quickly show you one of our results. One of our early results from our experimental evaluation in the river. So over here, what I'm doing is I'm plotting on the y-axis the normalized signal strength as a function of the estimated distance. And we ran some of these earlier experiments across different distances, specifically 24 centimeters, 34 centimeters, and 44 centimeters. So the plot over here shows you the signal that we are able to recover at 24 centimeters. As you can see, the signal peaks pretty close to where the ground truth is. So it's around 25 centimeters, even though when our ground truth is around 24 centimeters. It also shows that we're able to do something similar around 34 centimeters, 44 centimeters. And so what this shows is that our early results demonstrate that you could use backscatter to enable very high localization accuracy of the order of 10 centimeters. What is both very exciting and as well very exciting for us now is that there's so many open problems in underwater backscatter. So we've demonstrated the potential to reduce power consumption by many orders of magnitude. But there are a lot of interesting problems. For example, how can we scale the range and throughput of this new class of communication systems? Can we build multi-hop architectures so that we can enable communication over longer range? Can we also build accurate simulators that take into account the wealth of knowledge over the past decades of research in underwater acoustics and also apply it to this new and emerging backscatter IoT? How can we also reduce the energy consumption? We're now operating of the order of a few hundred microwatts, but actually backscatter in the limit should only consume of the order of nanowatts. So how far can we push it even closer to even extremely low power? And also, how can we go beyond net zero power to zero pollution? As some of you might know, these PZT or piezoelectric sensors have lead in them, but there's also other materials that exhibit the piezoelectric effect without having lead. And as we start trying to use IoT in the ocean, it is important for us to also make sure that we're not polluting the ocean. And there's many other applications in localization, navigation, and sensing. And what makes this exciting is all of these open problems and the potential to be able to have, to bring this technology to a lot of the applications from long-term sensing to coastal monitoring to aquaculture. I also want to say that we've released all of our code and schematics and tutorials that would allow people to reproduce our system end to end. It costs about, each of these sensors costs about $100. And so we invite you to be able to go ahead and build your own sensors, or and we're happy to also work with you on doing so. So far in this talk, I've told you about our work on batteryless underwater IoT. I want to quickly touch on another area that we work on, which is how can we send this information to outside the ocean? So what I've talked about is communicating in the ocean, but today is actually very difficult to enable direct underwater to air communication. So for example, if you have a sensor that wants to communicate with a drone or a receiver that is above the surface, it's very difficult for it to directly communicate through the water-air interface. And in fact, this is a standard problem in wireless underwater to air communications. And the reason is that wireless signals do not work well across medium boundaries. They work well only in a single medium. Now remember that so far we've been using acoustic signals. And so you might be wondering, why don't we use acoustic signals to communicate across the water-air interface? And the reason is that if you try to transmit acoustic signals, they will reflect off the surface. So they cannot cross the surface and you cannot use them to communicate with the outside world. Now, another option is to use radio signals. But the problem there is that radio signals die exponentially fast in water, which is why we use acoustic signals in the first place to communicate underwater. If you're working with compact nodes, with compact underwater nodes and airborne nodes, it's very difficult to be able to use electromagnetic signals to cross the water-air boundary. And today there's a bunch of workarounds, including relays, sonobuoys, or surfacing, but these are not cost efficient from an IoT perspective or scalable for a large number of sensors. And so one of the other technologies that my team has been working on is a technology that enables compact sensors to wirelessly communicate across the water-air boundary. And let me explain to you at a high level how this works. The way it works is that you have an underwater speaker which transmits sound. And because sound is a pressure wave, when it hits the surface, it causes a very small vibration at the surface. So to pick up these vibrations, we built a very sensitive radar. The radar transmits a radio signal, which reflects off the surface and comes back. And so we use it in order for us to measure the surface vibrations. So when the underwater speaker transmits a different sound, the vibrations of the surface are going to be different. And that leads to variations in the signals that are received by the radar. And so we use this to enable direct communication from underwater to air. And effectively what we've done is transform the surface itself from an obstacle to a communication interface. And we call this translational acoustic RF communications because it uses a translation from acoustic signals to RF signals. And it also gets the best of both worlds, acoustic for underwater and RF for the air. Now, one of the biggest challenges that we face is that natural surface waves can easily mask these micro vibrations that are on the surface. So even on calm days, ocean surface ripples or capillary waves have 2-centimeter peak-to-peak amplitude. This on its own is already 1,000 times larger than the surface vibrations that are induced by acoustic signals, which are of the order of few micrometers. So we started thinking about how we could sense these vibrations in the presence of even such weak ocean ripples. And here's our idea at a high level. Natural surface waves can be treated as structured interference and filtered out. So let me tell you what I mean by this. Naturally occurring waves, like ocean waves, are relatively slow. Their frequencies usually vary from 1 to 2 hertz. On the other hand, the acoustic signals that we're transmitting are transmitted at a much higher frequency, between 100 and 200 hertz. And because they are separated from each other in frequency, we can now use filtering. So the high-level idea of our solution is that we've developed filtering algorithms to deal with interference from naturally occurring waves. But of course, in practice, it's a little bit more complicated because of nonlinearities in the signal that we're getting back. But I will skip the details here, and I'm happy to take questions about it at the end of the talk, as well as elaborate on what we have in the paper. So I also want to show you one of the earliest systems that we built for this. Over here, you can see a short clip with the original acoustic transmitter and the radar receiver. And the underwater transmitter sends a signal, which is received and decoded, allowing us to communicate from underwater to the air. Then we started building on this basic idea, and we started testing it in different settings. So for controlled evaluation, we used a water tank. Over here, you can see the acoustic transmitter and our radar receiver. We also evaluated it in swimming pools, including in the presence of swimmers, as you can see here. And in swimming pools, the swimmers and the circulation currents were already causing continuous random ripples. Here's our acoustic transmitter. Here's our radar receiver. And we showed that you are able to communicate in these environments. But again, this technology is very exciting. It can communicate at lower throughput, at hundreds of bits per second. But what is more important is that it does so even in scenarios where prior systems for IoT could not communicate from underwater to the air, and even in the presence of surface vibrations that are 1,000 times larger. And so now we're also building on this technology to enable larger depths of operation, and in much more complex environments where we have less alignment between the underwater transmitter and the receiver. So far, I've told you about my team's efforts in building new technologies for underwater IoT. And I've also told you how we have open sourced our technologies to enable researchers and practitioners to build on our work. Over the next few minutes, I want to briefly tell you about our community organization and policy engagement initiatives. And I specifically want to highlight the Smart Oceans Conference, which I co-led in collaboration with my colleagues from the Woods Hole Oceanographic Institute. So the conference was sponsored by the NSF Convergence Accelerator Program, which focuses on use-inspired and goal-oriented research. And when we ran it last fall, it attracted over 1,000 registrants from over 300 institutions who came together on a shared platform. Our conference highlighted both the importance of use-inspired and curiosity-driven research. And I invite you to read the executive summary that came out of Smart Oceans that highlights some of these challenges. Now, I was told that we will soon hear the final decision of whether there will be an ocean track that is specifically focused by the Convergence Accelerator Program. But if it is chosen, then this will open up about between $40 and $80 million of fresh funding for use-inspired and goal-oriented research, bringing academics and industry to accelerate the field forward. Now, of course, given the importance of these problems, as I'm sure many of you know, the United Nations had declared this the UN Decade for Ocean Sciences. The US Committee on Ocean Sciences has also chosen batteryless ocean IoT as one of the ocean shots to highlight. My team has also worked for advocating this type of research by hosting at MIT more than 50 state senators and legislators, showing them live demos and telling them about the importance of these this area so that we can advocate for more funding and better regulations. We've also demoed our work to the US Director of National Intelligence, to the chairman of the FCC, and sometimes our impact initiatives led us to the White House. Here you can see a photo from a few years ago where we were invited to demo our research to President Obama. And this type of work is not only exciting.
Yep. Again. Your screen is frozen. I don't know how many slides you have left.
I have 3.
Okay.
So maybe I can stop and actually that is fine. I can probably stop over here and tell you about what else we're working on.
Okay.
So with this, I've told you about a lot of the work that we've been doing in ocean initiatives. My team also builds various types of wireless and sensor technologies, ranging from inside the human body to enabling robots to see things that are invisible to the human eye. And we work with oceanographers, we work with medical doctors, with climatologists, we also love collaborating with people across discipline boundaries because of all the exciting problems that we can work on together for climate, for health, for oceans. And I invite you to follow us on our social media accounts. We're very active in our outreach, but I also want to highlight that we have many openings for grad students, for postdocs, for research scientists, for staff, and we always love collaborating with new people across the board. And with this, I want to thank you. I wish I could show a photo of the amazing students that have worked on this. I've tried to highlight them a little bit through the talk. They are the ones who are behind this. They are now probably running experiments at the MIT Sailing Pavilion. And we're very excited about this moving forward. And with this, I want to thank you. I want to wrap up. Thank you for hosting me, and I'd be happy to take any questions.
Okay, thank you so much. So one question by Dale Chase, well, I guess it's more of a comment. With good design and implementation, the wake-up time should not be random.
That is not true, actually. And the reason it is not true is because, I mean, it depends on how much more expensive you want to make it. Are you trying to build an IC? Of course, in my team, we build ICs, but the whole point is to make this very, very cheap. But I do want to say that there's so many factors that impact the wake-up lag. In terms of there's multipath in the environment, so you cannot exactly predict what the wake-up lag is going to be. It might even change over time. There might be some more intelligent approaches, but even then, you would still want to use backscatter, which is our technology, because it is the net zero approach. What I also want to say is that we've been building ICs now in this space so that we can bring down the power consumption even to the nanowatt. There's a lot of important problems. So as Dale highlighted, maybe there could be ways of building it such that the wake-up lag is not a problem. We want to make sure as we're doing so, or as others are doing so, we maintain the ultra low cost of these approaches, because this is going to be key for the wide adoption of ocean IoT.
Okay, another question from Oceanic Acoustician. Nice that you can communicate waterborne signals to air. Can you do the inverse, capture with hydrophone radar generated signals?
This is a great question, and the answer that I will give is the one that was provided by my ONR program managers, a program manager. So there are some approaches for doing airborne to underwater. My team specifically has not been investigating them. We've been investigating the underwater to air communication, but there are other approaches for air to underwater, though I would say a lot of these are still mostly in the research phase.
Okay, are there any other questions? You may also untune and turn your video on. Okay, another question from Ben Gutzler. Hi, Ben. How much sound energy do you need to generate signals for the radars? Did the swimmers notice anything?
That is a good question. You could, in general, hear actually the sound. It's not, it doesn't blast the ear. So at the time, we were using even traditional underwater speakers, as you saw, the Bose hydrophone. So the Bose hydrophone maybe transmits a watt or a few watts. So it's not an enormous amount of energy. That said, as you start getting further, you need more energy. But the way you can also try to overcome it is by building more sensitive radars. So the radars that we're using, I did not go into a lot of details into them. These are millimeter wave, in the millimeter wave band. Millimeter wave is the technology behind 5G. And so the electronics are becoming so good on the RF side that by better signal processing, better electronics, you could even get the same range or more ranges, but at a lower transmit power. At the end of the day, it's a trade-off and you have a power budget. And one of the other things that I would say is this communication technology we've started seeing some papers study it theoretically, but there's also a lot of open problems that need to be worked on.
Dan, do you have a question?
Fadel, you always bring a smile to my science heart when I hear you speak. So thank you for that. Several years ago, we worked on a project we called Making Smart Sediment Grains, putting small MEMS-based accelerometers inside, not quite sand grains, but things about the size of golf balls. And as you can imagine, one of the limitations is battery technology. So do you have much experience coupling these with MEMS systems or networks where you can have imagine having different grains communicate with each other?
Great question, and great to see you, Diane. And thank you for the suggestion also, which allowed me to go through my talk. The answer is yes. We've incorporated different types of sensors. We've done pH, we've done temperature, we've done pressure, and we are building both analog and digital interfaces. And actually, our open source design is general purpose. It's almost like you have a microcomputer, and you can use that microcomputer to interface anything with it. We released our first prototype, which uses a microcontroller. We're now working on the second prototype, which consumes about more than 100 times even less power. And we're working on even a third prototype, and we do plan to keep these open source. And we're also happy to help with the incorporation or do it ourselves if it is helpful.
Thank you.
Okay. We have two more questions here. One from Miguel Candido. Great presentation. How are you thinking to scale up the use of radars to allow water-to-air communication?
So isn't that the question that is similar? Water? Oh, never mind.
Yeah.
So there's two ways. Actually, my own background is RF, is radar and RF signal processing. You could do so many different things. I mean, you could do AESA radars, you could do smart beamforming, you could cover a wide area, you could do different types of search. All of these have been developed primarily before from a radar perspective. I mean, this is a great question. Applying them to this problem is still, like, there's so many different opportunities and so many different ways to go. What is the best band to use? How many bands to use at the same time? Even these are still very interesting questions. And it's probably going to take us quite a good number of years to figure them all out. So there's a lot of research to be done.
Okay. One more question from Cameron Whitaker. Did you consider how the design would cope with algae and sediment interfering with the signals?
Yeah, this is a great question. I love all the questions.
There is another one coming.
we have not specifically looked at this yet, and mainly because we have not done it at a much larger scale. So we've been told that there are certain coatings that would allow you to mitigate this impact. One thing that I would say is that what we're building, the transducers that we're building, these are very similar ones to what is already used in mature underwater acoustic technology. So I assume these problems might have been explored in the past in this context, but not in this context. And there's going to be a lot of research at the intersection of what has been done before and what can be transferred, and how can we do this in a way that also maintains the ultra low cost of these designs, because this is going to be key. Maintaining the low cost is going to be key. So we've thought about it. I do not have an answer. You might have an answer, and I'd love to hear it from you.
Okay. From Oceanic Acoustician again, would it be useful to use resonance of micro air bubbles near surface to improve waterborne signals? Explorative question, though. I know air bubbles are very reflective, but could be done and used.
Okay, again, fantastic question. We've looked at this a little bit. We've read a little bit of the literature. The answer is you might actually get something both for like uplink and downlink if you were to use something like that, because so what some people have done is they've tried to even heat these bubbles and use them as a way to like create pressure waves that can, by exciting them at resonance. We haven't specifically went down this path, but I would be very excited to see what would come out of it.
Okay, and Jack Sedelmeyer say, thank you, fascinating to think about the possibilities. And Oceanic Acoustician says, nice. Are there any other questions or? Okay, so I think this is it.
I promise to tell you why I don't have a good internet, even though usually at MIT, if I were in Cambridge, Massachusetts, where I usually live. So I'm actually, I actually am not in the US for now. I had to travel to, actually due to a family medical emergency, I had to travel to where my family lives, which is in Lebanon, Eastern Mediterranean. I grew up in a port city, so I'm used to the sea, and this is also why I love working on this work as well. So I had to fly because one of my family members was in a critical condition, and I was very worried. And it has been a difficult few weeks, but I wanted to make sure that I attend, that I still do this talk and get these questions, because I expected the questions to be great. There is a good end to the story. Actually, my family member recovered. They're doing great. They were discharged from the hospital. When they went in, it was a very difficult situation due to COVID, actually. And so I'm actually flying back this weekend. But stay safe, everyone. Take care of yourselves. My family members were taking care of themselves, but where we live, COVID is everywhere. And so it was actually quite challenging for them to take good care. And I hope that I will be able to visit in person after this is behind us, and be able to collaborate with folks and meet people in person. So thank you very much for hosting me. And I really appreciate everyone's questions and the invitation.
Thank you so much, Fadel.
Yeah,
we really appreciate you still doing this presentation for us.
Yeah, full health to the family. Glad to hear the good news. Few nice more words. Thank you so much, Fadel. It's very fascinating. I'm also working on a thesis that has underwater applications from Cameron Whitaker. Oceanic Acoustician says, nice presentation, the best for your family. Great presentation from Mason. And okay, so Oceanic Acoustician has another question, if you may. And Marcus Pereira, thank you for the presentation, amazingly interesting material. Okay, so everyone, you can see Fadel's email in the chat that you can follow up. Whoever needs to leave, thank you so much for joining us and for the patience throughout the seminar. And thank you so much, Fadel, for joining and sharing your work with us. It's very fascinating.
Thank you. Bye, everyone.